Good evening, boys and girls. Welcome to another lesson on Technical Sciences, grade 12. I hope you had a really beautiful morning and afternoon. I am so glad that you could join me for this lesson. And we are continuing with electric circuits, and is the topic that we've been dealing with since Monday. And I really think that we are doing quite well. And today we are continuing and we are looking at two sections as per the examination guidelines, and we are going to look at ohmic conductors as well as non-ohmic conductors. Remember, we must be able to give the differences between those two, meaning your conductors that are ohmic as well as those that are not ohmic, and we will have a graphic representation as well so that we see how these ohmic conductors are actually different from non-ohmic conductors, and as well how the graphs of those actually look. And we are also going to look at the cost of electricity. In other words, we are going to check how much is it going to cost you to use a certain appliance for a certain period of time. If you know the power rating of that particular appliance and how much a kilowatt hour actually costs. So we will be talking about all of that. So I hope you have your pens ready, you have your paper ready, and maybe some snack on the side, and you are ready to get learned. Right. In the overview of the lesson, we are going to quickly revert back to what we need to know as per the examination guidelines for this section on electric circuits. And then in the features of the topic, we will still be learning electric circuits, but we will be looking at questions from previous examination papers so that we actually see how these questions are asked and how your answer must be presented, because I told you I am hoping that you will be able to totalize these question papers, because it is definitely possible, my learners. We've had a couple of learners in the past that got something like 148 out of 115 paper 1, 147 out of 115 paper 2. So I know that you can also make it even better. You can take it to 150 over 115. So hence we are doing this and we are practicing some more and more. And that is why I will also be giving you more tips on how to prepare for the examination for this particular topic altogether. Right, so we shoot straight into what is expected of us in terms of the examination guidelines. And remember, we must be able to state Ohm's law in words. We have actually talked about that before. And then we must know the relationship between current, voltage, as well as resistance when the temperature is constant. So we must know how they relate to each other. What happens to the current when the voltage increases, or what happens to the current when the voltage decreases at a constant temperature. So we must be able to establish those types of relationships, and we must be able to state the difference between ohmic and non-ohmic conductors, and we must be able to give examples of each. And that is essentially the core part of the lesson today. We will be looking at those examples, and then we must be able to solve problems using R is equal to V over I for series circuits and parallel circuits, and even more for a circuit that has a combination of resistors that are connected in series and parallel in one circuit. And then we must be able to use series and parallel resistors in combination with Ohm's law. Then remember, a definition that you are required to know here is the definition of the EMF, and that is the potential difference across a cell when the circuit is open. Definitely know this definition. We will ask you. It is the potential difference across a cell when the circuit is open. And then you must be able to define again internal resistance. And that is the resistance inside the cell when current flows through it. Right? Furthermore, we must be able to define power. And in terms of electricity, we know it is the rate at which electrical energy is converted in an electric circuit. And we will quickly, when we get to the section on power, because we will talk about power again today extensively, because it is the core section for this particular lesson, because we haven't treated much of it. And I know that some of you are actually thinking about the definition of power as we have done when we're dealing with the section on work, energy, and power. And you defined power as the rate at which work is done. So we will have a discussion around that, because here you see a different definition or a different interpretation of rate, because now it is in terms of electrical energy. We recall again the SI unit of power is definitely a watt that is represented by a capital letter W, but we know the practical unit of power is kilowatt hour. Right, for example, when we buy electricity, we know it is given the units that we get practically are those kilowatt hours. And then we must be able to solve power problems using the formula power is W over delta T. Power is equal to VI. Power is equal to I squared multiplied by R, or power is equal to V squared divided by R. And we use that to calculate power. And the variables that are involved is the work or the energy or the heat, the time, the voltage, the current, as well as the resistance. And I told you again, my dear learners, we could ask you to explain what is meant by 1 kilowatt hour. And we know 1 kilowatt hour, or simply a kilowatt hour, refers to the use of 1 kilowatt of electricity for 1 hour. Go together, my dear learners. So we must be able to interpret that. Then we must be able to calculate the cost of electricity usage given the power specifications of the appliances used, as well as the duration, if the cost of 1 kilowatt hour are given altogether. And then the heat produced by the resistor in a circuit is given by W is equal to I squared R delta T. And there's actually more formulas that we give you in your formula sheet, where you can actually calculate the heat that is dissipated or the energy that is dissipated by a particular resistor altogether. Right, so we will talk about that. Now, let us get to the core part of this lesson, which is ohmic as well as non-ohmic conductors. Now, when we talk about ohmic conductors, or when we talk about ohmic resistors, we are talking about resistors that obey Ohm's law. Now, let us remind each other, what are we talking about when we talk about Ohm's law? Or rather, how to state it. It says the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. In simple terms, it tells me that when the current increases, rather when the potential difference across the conductor increases, the current is also going to increase at constant temperature altogether. That's what it says, because it says that potential difference across the conductor is directly proportional to the current in the conductor at constant temperature. What are the implications of that? The implications are that if you were to double, for example, the potential difference, then the current in the conductor would also double. If you were to make the potential difference in the conductor 4 times as much, the current in the conductor would also be 4 times as much, only if the temperature is constant. In other words, the resistance does not change. The resistance becomes a constant value, right? So we continue and we say, okay, if it is directly proportional, it means that if I were to draw a graph altogether, a graph of current versus potential difference, then I'm expecting to get a straight line graph that is going to cut through the origin altogether. It must be a straight line. At the same time, it must cut through the origin altogether. What does that mean if it cuts through the origin? It tells me that if the potential difference across the conductor is 0, then the current is also going to be 0 altogether. And therefore, that signifies an ohmic resistor. It signifies a resistor that obeys Ohm's law, or simply it signifies a conductor that obeys Ohm's law. And therefore, because it obeys Ohm's law, then we say it is ohmic. Are we together? And then here we have that graph. It's a straight line graph and it is linear and it cuts through the origin altogether. That is why it tells me when you double the potential difference, then the current is also going to double. Are we together? Right. If you have if you double the potential difference, the current is also going to double. If you have the potential difference, the current is going to have, and so on and so on. So this one, the first graph, that definitely represents a graph of an ohmic conductor, or a graph of an ohmic resistor, because basically there I can see that the potential difference is directly proportional to the current. Now, when we have a non-ohmic conductor or a non-ohmic resistor, it is the exact opposite of an ohmic resistor. So either it is ohmic or it is non-ohmic. Remember, if it is ohmic, we say it obeys Ohm's law. What does that imply? It means if it is non-ohmic, then it does not obey Ohm's law. There it is. It does not obey Ohm's law altogether. And a linear graph will not be obtained. It means you won't obtain a graph like this one. Can you see there? This graph is not linear. The fact that it's not linear already tells me that this potential difference and this current, they are not directly proportional. Remember, if you do not obey Ohm's law, if a conductor does not obey Ohm's law, It means the potential difference across the conductor is not directly proportional to the current in the conductor, and we can definitely see that altogether. So this also a graph that shows me that this resistor is non-ohmic, because if it were ohmic, I would expect a line graph, and that line graph is going to be straight and it will cut through the origin, so which is not the case here. So this represents an conductor or a resistor that is non-ohmic. The same applies to the third graph. This third graph definitely represents a resistor that is non-ohmic. It represents a resistor that does not obey Ohm's law. Altogether, it is non-ohmic. This one is also non-ohmic. That one was ohmic. So I'm here on the third one. It is non-ohmic. It does not obey Ohm's law. The potential difference across the conductor is not directly proportional to the current in the conductor, and we know why that is the case altogether. Why is that the case? Because this graph is not a straight line graph, it is not linear, and therefore I'm not getting a constant gradient altogether. So there is no direct proportionality. If the gradient was constant, then I would have a straight line graph that cuts through the origin. So this does not obey Ohm's law altogether. Then we must be able to give examples of ohmic resistors. So pure metals, when we give examples of ohmic, we talk about metals that are pure. And lastly, a form of carbon that we call graphite. These are examples of ohmic conductors altogether. So you must be able to give us at least two of these ohmic conductors, examples of two, and we are saying pure metals. Remember, my dear learners, don't just say metals, ne? Because metals are not necessarily the same. Some are actually in the form of mixtures and so on altogether. It's just that you won't see it's a mixture. So simply, it has to be a pure metal. Know this, it is there in your examination guidelines. And you must also know that graphite is a form of carbon, and it's an ohmic conductor. In other words, it obeys Ohm's law. And there we say pure metals such as copper obeys Ohm's law as long as temperature remains constant altogether. So that is that. Carbon, which is in the form of graphite, although a non-metal, also obeys Ohm's law. And I'm really expecting you to talk about graphite. I don't want you to talk about carbon, because carbon has many forms. Diamond is a form of carbon, but it does not conduct electricity. So the appropriate answer will be graphite altogether. And other materials, for example, your diodes that you are commonly used to, your filaments in light bulbs altogether. Those are examples of conductors that are non-ohmic. They do not obey Ohm's law. Are we clear? So these ones, the diodes, as well as the filaments in light bulbs. And don't just write filament, we must tell us which filament is that. Filaments in light bulbs. Those are good examples of non-ohmic conductors. And I've chosen these two because these are the ones that you are commonly used to. Altogether, you're not really used to transistors and semiconductors, although you know what semiconductors are. from one of the topics that you do, but you don't really use that altogether, right? So talk about diodes and filaments in light bulbs, and 2 is enough. We won't really ask you for more than 2 of these examples of either ohmic conductors or non-ohmic conductors altogether. Then I want us to talk about power. And there I've given you a definition of power. And I say power is defined as the rate at which work is done. And you know this definition altogether. And the fact that we define power here as the rate at which electrical energy is converted in an electric circuit is the same thing, is the rate at which work is done. So to avoid any confusion, let us stick to one definition for power, and we will say power is the rate at which work is done, and you will get all your marks altogether. So do not differentiate it. Now you are dealing with work energy and power. Now you are dealing with electric circuits. That is simply going to confuse you. I want you to collect all your marks. So we go back to the definition that we are used to, and we know that power is the rate at which work is done. And the rate at which work is done, it means power is then W divided by delta T. So this is one of the formulas that we use to calculate power. And even more so, my dear learners, we know that the definition of power actually originally emanates from that particular formula, because it clearly shows us that it is the rate at which work is done. Then, if you do some mathematics and so on, which is not necessary for you, you can find that power is then given by V multiplied by I. It means in a circuit, power will be given by the potential difference multiplied by the current, or the power will be given by current squared. So you'll take the value of current and square it and multiply by the value of the resistance. And then power is also given by V squared over R. So the potential difference squared divided by the resistance. So this is how you would calculate power. And remember, what are the units of power? Power is measured in watts. It's measured in watts. And we know watt is represented by a capital letter W, right? Not a small letter, W. So now let us go to questions that now come from previous examination papers, and they incorporate power as well as some of the things that we have learned since Monday. Now they say, in the circuit represented above, the battery has negligible internal resistance. And remember, we must know how to define the term internal resistance. And we said it is the resistance inside the cell when current flows through it. It is the resistance inside the cell when current flows through it. So it's there when current flows through it. That resistance that is experienced inside the battery, we call it internal resistance. So here they're telling us that it has negligible internal resistance. So we take that there is no internal resistance. Based on this, my dear learners, the 12 volts, we can definitely tell that it is the EMF altogether. It is the total potential difference across the circuit. So that gives us a value of 12 volts. So we have 12 volts. Now let us check what is going to happen here. I told you always start at the battery. Now here I have total current all the way, total current all the way, total current. So this ammeter is measuring the total current. Altogether, it's measuring the total current in the circuit, and that is why it is always best to start where, my dear learners, to start by the battery. This is definitely a battery, my dear learners, because I have two cells, they are connected to each other and they are correctly connected to each other. Why? Because I can see that the negative terminal of this cell is connected to the positive terminal of the other cell. So the connection is 100% correct. So all of the electrons, all of the negative charges, all of the current has to go through the battery so that it can pick up that electrical energy of 12 volts, the EMF, the electromotive force. So it's all the current, there's only one way, all the current, ammeter is connected in series and it measures the total current, and they've shown me there that this ammeter is measuring 0.5 amperes, and we know it is the total current. Total current, total current, total current. So here I have the total current as well. In other words, this resistor is connected in series. Remember I said, if a resistor gets the total current, then we know it is connected in series. Again, remember, because it's receiving the total current, it means on this 18 ohm resistor, the current that is going to pass here is going to be 0.5 amperes. And we can actually ask ourselves that, okay, how many volts did you use here altogether? We can actually calculate how many volts were actually used to move 0.5 amperes of current through an 18 ohm resistor. So we need to know that. So it is the total current, the total current, the total current. And now when we get to this point, I can see that some of the current will go in that direction through this conductor, and some of the current will go down here through resistor R. So the current is going to divide. So some of the current will flow through the 24 ohm resistor. Some of the current will flow through the resistor, which is called resistor R. Then all of the current, my dear learners, through the 24 ohm resistor will come like this and get to this point. The current through R will come through and get to that point. And then from there, I know that all of the current meets again, so I will have the total current. Now, what do I know? When the current divides, I know that some of the current flows through there, some of the current flows through resistor R, but I will not have any current that is flowing through the voltmeter. Why is that the case? Because the voltmeter has such a high resistance. Even the electrical energy carried by the electrons will never allow your electric current or your electrons to pass through it. So all of the electrons will pass through resistor R altogether. So because the current has actually divided, it means the 24 ohm resistor is not getting the total current. Resistor R is not getting the total current. But if I add the current through resistor R plus the current through the 24 ohm resistor, I expect that to be the total current altogether. Right. Now, what do I know again? I know that the voltage that is used here will be exactly the voltage that is used there. How do I know that? I said to you, all resistors that are connected in parallel, they are going to have the same potential difference. So remember that if the value of V is a certain value, then the value of the voltmeter that is connected on the 24 ohm resistor is going to be the same. Why? Because these resistors are connected in parallel. So they are current dividers. They are not potential dividers altogether. So remember, when they come here, all those will go with their volts there. All those will go with their volts there, and the volts are the same altogether. So now we understand the circuit. Let us go and answer the question. We are required to state Ohm's law in words. And we are definitely able to do that. We know Ohm's law states the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. And that is going to give you 2 marks. And there's the definition. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. And there we get 2 marks. Remember, my dear learners, all the keywords must be there and they must be used in the correct context for you to get your marks. If you don't use them in the correct context, even if they are there, you are not going to get a mark, because not using them in the correct context makes the scientific meaning to be lost. So I've told you that we have shifted in terms of how we mark, and we are definitely moving away from part marking, where we give you 1 mark for the first part and give you the mark for the second part, provided the first part is correct. So we are moving from that. Definitions are 98% of them are now either a 2 mark or a 0. Other laws are 3 marks or a 0. So be able and be wary of that. Then we are required to calculate the potential difference across the 18 ohm resistor. Remember, my dear learners, if I want the potential difference, you will definitely agree with me that, Menier, I want to know the voltage that is used to move the current through the 18 ohm resistor. So remember, when I want the potential difference, I want the voltage. I want to know the number of volts that were used to move that amount of current through the 18 ohm resistor. So for 6.2, I think we can easily calculate it there. We have space. So let us do our question 6.2 here. We will start by saying, I want to know what are the volts that are used here. Meaning, if I had a voltmeter, and let me call it voltmeter 2. If I had a voltmeter 2, what would be the potential difference here? Now, my dear learners, when you start this question, I told you, you have a resistor in series and you have those that are in parallel. I told you the best trick is always to start with your resistor that is in series. And that is why, luckily with this question, it is leading us. They are starting to ask us questions where we start working on the resistor connected in series. Then I'm going to say, okay, I know the resistance there is 18 ohms. I know the current is 0.5 amperes. So I want to know how many volts were used in here. I want to know the potential difference altogether, which is the voltage. So R becomes, okay, let me just write my answers in a nice color that we like at Africa Teen Geeks, and that is purple. right? So our answers are in purple. So we'll say R is equal to V over I. Now let us remember our triangle. It says R is equal to V over I. Then we know the resistance here, it's 18. We know the current is 0.5 amperes that is passing through here. So I want to know how many volts were used, and I will say that I am definitely using 9 volts because it will be, when I want the value of V, it will be R times I altogether. So if I want this value, I will take the value of R multiplied by I, then I get 19, rather I get 9 volts. So that is likely to be 3 marks. Sometimes, you know, for that we could give a mark, so it could be 4 marks. Then that will be the reading on there, and we agree that it gives me 9 volts. Now, if I'm getting 9 volts here, what does this tell me? It tells me we know the electrons were coming and coming and coming and coming. At this point, they still had their 12 volts because they were moving freely through the conductor, moving freely through the conductor, through the ammeter freely. So when they got here, they actually were still having from where it is connected, the voltmeter, they were still having 12 volts. So we used 9 volts in there. In other words, when the electrons moved through the resistor, they were at 12, moved through the resistor, they used 9. So it means when they exit, they will have 3. And that is why the potential difference, the difference between the potential at that point is 12, the potential at that point it's 3. So the difference in potential is 12 minus 3, which gives me 9. What does this mean, my dear learners? It simply tells me that they were coming through with 12 volts all the way. 12 volts there. When they moved through here, they used 9 volts. When they exited the charges, then there were 3 volts. Then they came through with their 3 volts. Those electrons that divided and went up, when they go, they will still go with what? Let me call this V3. When they go up, they will still use what? 3 volts. Those electrons that follow that route to the 24 ohm resistor, they are going with their 3 volts. And those that are going down, they're still following that route through resistor R, and they're coming with 3 volts. It means the reading on that V is going to be 3 volts as well. And remember, it must be the same between them because resistors that are connected in parallel, they only divide the current, but the potential difference does not divide. That is why there on V3, I have 3 volts, and there on resistor R, I also have 3 volts. Right, we continue. We are required to calculate the power dissipated in the 18 ohm resistor. Can you see what they're saying there? The power dissipated. So this is just a fancy word that we use, dissipated, and we can definitely calculate that. Remember, my dear learners, we have quite a number of formulas for power. We have power is V times I. Another formula we have power, it's I squared multiplied by R. We have another formula which says power is equal to V squared over R, and they will all give us the same answer. So in 6.3, or rather, let me just check. Yes, it's 6.3. I can use any of these equations. Let's try P is equal to VI. Then I know my P is the power that I'm looking for. So the V that is used there, I calculated it, it's 9. And the current that is moving through here is 0.5. So it means I have 4.5 watts. I could have went further, my dear learners, and said, not further, I could have used another method. I could have said power is equal to I squared multiplied by R. And then if I use this one, I will say I squared, the current through here is 0.5, and I'm going to square that, and I will multiply by the resistance there, which is 18. And 0.5 times 0.5 is 0.25 times 18, it's a quarter of 18, and that will still give me 4.5 watts. Another learner could have said, okay, Meneer, I will use power is equal to V squared over R. Our V there, it's 9 squared, and I will divide by R, which is 18. And 9 squared divided by 18 definitely gives me 4.5 watts. So any of those formulas gives you the same answer. Right, remember the unit is watt and it's a capital letter W. Then we are required to calculate the reading on voltmeter V. So voltmeter V is this one. We must get the reading on voltmeter V, and that is 6.4. Now, my dear learners, this does not necessarily have a formula. You could go the long way around and use formulas, but here we are basically testing your understanding. And what we know is that if I want the value of V, the voltage used here, I know that in total I had 12 volts, and there I used 9 volts. So it means the remaining volts, I had 12 volts, I used 9 volts through the 18 ohm resistor. So it means I'm going to be left with what? With 3 volts. And these 3 volts are the ones that will be used through our parallel resistors, meaning the voltage that will be registered by V. In other words, I can say, just to put it simple for myself, I can say to get the value of V, I must actually take V total, which is the EMF, and substitute the voltage that was used on the 18 ohm resistor, or VS for the voltage that was used in the second series resistor. So the total is 12 minus the one that was used there, it's 9. So 12 minus 9 is definitely going to give me 3 volts. Are we together? Another way that you could have calculated this, my dear learners, it's very long. It would require you to actually calculate the current through there, but that would have now required you to actually know the value of V, which is 3 volts. And when you get the current there, you could calculate the current there as well, but you still don't know the resistance. So the fact of the matter is, this is the best way to actually get to the final answer. And this is most likely to be 3 marks if we decide to give the formula to check if you are actually able to understand what is being asked of you. Then they tell us R is an ohmic resistor. What do we mean if it says an ohmic resistor? It's a resistor that obeys Ohm's law altogether. Number two, if it obeys Ohm's law, it means the potential difference across the conductor or across this resistor is directly proportional to the current in the resistor at constant temperature. We are required to calculate the current in the 24 ohm resistor. So we must calculate the current that is moving through here. Now remember what we have done, my learners. We have actually calculated in 6.4 that the reading there is 3 volts. If the reading there is 3 volts, automatically the reading of the voltmeter that would have been connected on this 24 ohm resistor would be 3 volts because they are connected in parallel. So the voltmeters would read the same value, or the potential difference would be the same because they are not potential dividers. So they don't divide the potential. That is why they are both 3 volts. Then what we would then say here is we know the total current is 0.5. So if I know what is the total current here, then if I get the current here, then I will say the total current there, and I will subtract the current that is moving there. Then that would give me the current through the resistor R. So we are now on 6.5.1. Right, 6.5.1. Now, I'm focusing on the 24 ohm resistor, right? And I will say, I'm just writing it there so that you can see what I'm talking about. R is V over I. The resistance there is 24. The voltage there is 3 divided by the current. Then if I want the current, then the current is going to be a value which is determined as I, it's V over R. So I must take the value of V, which is 3, I must divide by R, which is 24. Then I'm going to my calculator, and I am saying there, this is 3 divided by 24. And I see that it gives me 0.125 amperes. Then I quickly just write it there. The current flowing through here is 0.125 amperes. Now remember, my dear learners, at this point, okay, that's not nice. At this point, where the current starts to divide, the total current was 0.5 amperes. So if out of the 0.5 amperes, 0.125 amperes goes through there, then it means the current that goes through resistor R will be 0.5, and I will subtract that. So the current, remember, I'm calculating the current. And now I'm looking at resistor R. Oh, okay. No. We simply wanted, good. We simply wanted the current that was moving through the 24 ohm resistor. So we knew what was the resistance, which was 24. We knew what was the voltage, which is 3 divided by I. So the current there is 0.125 amperes. Then the last question is, we must know how to calculate the resistance of R. To get the resistance of R, Firstly, what we need to be able to do is, I know the value of V. I want the value of R. So I need the value of I. So if I have V, I have I, then I will calculate R. So let us check through R. Firstly, through R, I don't know the current. So if I want the current through R, I will say that current, it's actually, I must take the total current, the current through R will be the total current, which is 0.5, subtract the current that is moving there, which is the current that is moving through the 24 ohm resistor. Now, these subscripts are not necessary. I'm just making it easy for you. And the total current is 0.5 minus the current that is moving through the 24 ohm resistor. We calculated it's 0.125. Now, obviously, then it means if I take 0.5 and I subtract 0.125, it means the current there is going to be 0.375 amperes. Good. And then we say, okay, I know the current now is 0.375 amperes. And this makes sense, my dear learners, because the current there plus the current there must give you the total current, which is 0.5 amperes. Then to calculate the resistance, I will just say R is equal to V divided by I. And the resistance, there is what I'm looking for. The voltage, I definitely know that it is 3 volts divided by the current there, it's 0.375. And then 3 divided by 0.375. Just go to our calculator. We say 3 and we'll divide by 0.375. And we can see that the resistance there is 8 ohms altogether. So you are likely to get marks there and marks there altogether. So this type of a question could be something like 5 marks. So the resistance there is definitely 8 ohms. What a beautiful question, eh? Then, thought I'd use this space. Last part, let us talk about the cost of electricity. And maybe I must just write a formula there quickly as I explain to you. That you put to make it easy for yourself. Right. Now, here we know, commodities. When you talk about commodities, we are talking about, things that are sold, that are valuable, and so on, like your gold, like your bronze, and so on. So commodities are usually sold in certain units. For example, if you look at sugar, it is sold in kilograms most of the time, or grams, and you pay a certain amount for each kilogram or gram. fuel, for example, your petrol, your diesel, your paraffin, you usually buy it in liters, and the cost is in liters as well. So, for example, if you look at petrol, it is expressed as 12 rand per liter and so on. So that is the cost per liter of that particular petrol. Now, when it comes to electricity, it is still the same thing altogether. And with it, when we buy, we get it in units that we call kilowatt hour, kWh. We call that kilowatt hour, not kilowatt per hour, it's kilowatt hour. And we can give the cost per kilowatt hour, and we can say it's the cost per kilowatt hour. For example, it could be 80 cents per kilowatt hour. When you see something like this, you can see that it's giving you a cost per kilowatt hour. Why are we saying it's per kilowatt hour? Because it's 80 cent dot kilowatt hour -1. So kilowatt hour -1 means per kilowatt hour. Now, we can ask you to calculate how much it will cost you to use electricity. Now, for you to know how much electricity, how much you are going to pay for the amount of electricity that you have used, there are important things that you must know. And I want this to be clear because we have a cost of usage. When I talk about the cost of usage, I am talking about how much is it going to cost you? Is it going to cost me 15 rand? Is it going to cost me 10 rand? Is it going to cost me 20 rand? For the amount of electricity that I have used. So we have a cost of usage. So the amount that you are paying for what you have used. And to know how much you are going to pay for what you have used, it means I am talking about the amount. So simply the amount, not the amount per kilowatt hour. I'm talking about the amount that, you know what, I was using this kettle and I used it for 3 hours, and this is the amount that I'm going to pay. For example, I'm going to pay 2 rands for that. That is the cost of the usage. And for me to be able to figure that out, I need to know the cost per kilowatt hour, because electricity is sold in kilowatt hours altogether. So I need to know how much does it cost per kilowatt hour, and what is the power rating of that particular appliance, and for how long do I use it altogether. Now, let us say we want to calculate the cost of actually using a light bulb, that has a power rating of 100 watts, and the cost is this one. It's 80 cents. It's 80 cents per, remember, it's per kilowatt hour, and I use that light bulb for 2 hours. Now the cost of usage is going to be given by the cost per kilowatt hour, and I don't want to remove the units for now. Remember, when we do our calculations, we normally just remove the units. So this is 80 cents per kilowatt hour. So I just want to show you how the units actually cancel here. Per kilowatt hour multiplied by the power rating. Now our power is given in watts. So I can't work in watts here because I'm dealing with kilowatts altogether. So I need to take the 100 and take it to kilowatts. And we know if I go to kilo, a kilo is 1,000 times more than a watt. So it means if I want to go from a watt to a kilowatt, then I have to take the 100 watts and divide it by 1,000. And that is going to give me 0.1 kilowatt. Altogether, this will be 0.1 kilowatts. So I will multiply there by 0.1 kilowatts, and I will multiply that by 2 hours altogether. So what does this give me? It will give me, this will be equal to 80 cents per kilowatt hour. Just want to show the practicality of this. Per kilowatt hour, remember it's -1, multiplied by 0.1 times 2, it will definitely give me 0.2, and kilowatt multiplied by hour, it's kilowatt hour. Then 80 cents multiplied by 0.2, this is then 80 multiplied by 0.2, it will give me 16, and that will be 16 cents. And that's where it will end. Why? Because kilowatt hour, -1, kilowatt hour, you know mathematically it's similar to +1. So kilowatt hour -1, kilowatt hour +1, then we know mathematically, my dear learners, it's -1 plus 1, it's 0. So kilowatt hour to the power of 0, it's 1. So it will be 16 cents altogether. So mathematically, this multiplied by that gives you 1. And then 80 cents multiplied by 0.2 gives you 16 cents. So the cost will then be 16 cents for 2 hours. If the cost is 80 cents per kilowatt hour and the power rating is 0.1 kilowatt and you use the electricity for 2 hours. So just keep this formula in mind and you will get a mark because you have just written it in full. We don't really give you a formula sheet for that. So be able to work with that altogether. Such a beautiful section that we dealt with today. Right, 15 marks. At the end of the year examination, in fact, ±15 marks. So prepare thoroughly, know your circuits, be able to work with power, be able to deal with the cost of electricity. So tomorrow we will be dealing with calculations of the heat dissipated, the energies, and so on. So we will get circuits around that. Thank you so much. Send me questions to stemdigitalschool@africateamgigs.co.za. Altogether, if you want me to assist you with anything and in preparation for our question and answer session. Thank you so much for tuning in and enjoy the rest of the evening.